Okay, let's talk about a few final things in our homework too. A few things minor detail I would like to go over with you uh, before you turn in your homework assignment. And go over 500 observation and trying to find out what is a proper statistic distribution function to put into processing time. Second, we're going to discuss the station failure logic. And third, during the failure period, how we can use seize and release maintenance engineering during this time as a repairman. Last two is introduce some of the output statistic and state variable statistic and explain a little bit what are the differences between them. For example, the work in progress inventory, or the time to stop the simulation, and how long the simulation actually runs, and we can using output statistics to let it becomes a part of your result grid. And the next we're going to talk about how these output statistic or state variable statistic can be used to set up a response in your experiment, okay, and use that as the objective function to optimize your system. So we go this detail one by one. First is the 500 observation. In our homework assignment, we give you 500 observation in a data file. We call it unpipe time, and in a TXT format or a CSV format, either one of them. We're using tools to actually figure out what is the proper statistics, so a distribution function. Let's go to your syllabus page on your Canvas. Go down and check. There's a general tool to the class, and the first one called Easy Fit Input Modeling Software. And if you click on it, it brings you to the software website so you can download and install. Here I already have it installed, so we're going to start this software. The software looks like this. So first things we're going to use is going to grab a data for us. So I have it on the desktop already here. So just going to load it up. Okay, we're going to import all the rows into this here. Okay, so all the data, actually we have 500 observation over here. We're trying to figure out this with each data, what is the proper distribute function to describe this data. So here we're trying to do is go into the analyze, the fit distribution. It will choose all the information, all the rows from this variable one. Okay, so we're going to click OK. It takes a while to figure it out. So the software actually will, for each different distribution, they're trying to figure out the parameter according to that. So these are the parameters to describe that distribution. Okay, and for example, you want to fit it to a normal distribution, for example, gamma distribution, Erlang distribution, log normal distribution, and these are the corresponding data for it. Okay, and beta distribution, and so everything pretty much exponential distribution, for example, Okay, exponential distribution is not a very good fit, and so on and so forth. And they will try to figure it out. Okay, and also it gives you a summary for each one of the distribution if you want to choose what are the corresponding parameters for that. Okay, so for example, beta or, but here's the question: what is the best fit among all these, what do we have, 61 continuous distribution function? So we go to the goodness of fit tab and figure out for each one of the distribution function, we have three different type of tests. One we call the Kolmogorov-Smirnov test, is a non-parametric test, goodness of fit method. Second is Anderson-Darling method, and third is a chi-square, which is very standard for the discrete data. But for the continuous data, Kolmogorov-Smirnov and Anderson-Darling will be a little bit better description for that. So if I choose and click on any of the test method, it will show you the ranking of that method. Okay. So these are the things you can decide. For example, I want to choose Kolmogorov-Smirnov test, and Johnson SV method will be the best and show you what is the sample size, what is the statistic p-value, ranking, and all the parameters over here, and show you what is the good things about that. Okay, so here we have all this, and for example, we choose beta distribution, okay, and give you the statistic, critical value, and so on and so forth. So we can decide, well, for the beta or normal or exponential, whatever you decide, what is the best method. Okay, so we can go back to see if we want to choose beta method. This is alpha 1, alpha 2. A is the smallest value, B is the largest value. For example, this is 9.6, so I'm going to go to my model, and for example, go ahead right here and put it in the processing time. Instead of using the original processing time, we're going to start using a random beta, for example. I'm going to just show you one. Okay, random beta, we just need a alpha 1 and alpha 2. So we already have alpha 1 here, 9.6 something. What is the other one here? Alpha 2 is 12.8. For example, and the smallest value will be the offset for your starting point, so 1.66. Illustrate that and plus. So here we have a range, okay, multiplier. So this is will be B minus A, the largest to the smallest data. So here what we have, oh sorry, here what we have is the 18.05, 1.66, 0.05, so we can say 18.05 minus 1.659. So that's the range actually. So the random beta distribution, the outcome is between 0 and 1. So this is the skill factor. Okay, skill. This part is skill, and this is actually the shift, basically the okay. So smallest to the largest, the difference is the skill, and then the offset is the smallest value for that. So we finished this set of, all right. Our next objective is trying to model the station failure logic. And our homework, we assuming this special workstation has a failure between. So I think the mean time between failure is 12 hours. And the repair time after failure is 1.5 hours. Both follow exponential distribution. Here I want you to open up the reliability logic. Instead of no failure, I will say I will have a calendar base because it's based on time. So uptime between failure is basically, here as we said it, is 12 hours, exponentially distribution, and time to repair is basically another exponential distribution. Sorry. Exponential distribution of 1.5 hours, for example. So that pretty much finished the failure logic. However, during this time for repair, 1.5 hours, I need to seize a maintenance engineer. So here what we have, is a worker. We're going to add another resource. And simply call it engineer. Okay, we have this maintenance engineer. We only have one of those. And if you look at 3D manner, we can see that's the maintenance engineer with a work suit. We're going to seize this engineers during the failure. So come back to the special workstation. We're going to add two add-on process during that time. One is when the station is filled. So we're going to add an add-on process. So the special station is filled. We're going to add the add-on process right here to seize the maintenance engineers. Okay. Seize the engineers. Also, going back here, for after the station got repaired, we're going to release that engineer. Okay. So that's very easy. So for that, here what we have is every 12 hours based on the calendar time, every 12 hours I have a value event. And after that, I'm going to delay for render an exponential on the average of 1.5 hours to repair. During this time, right after fill, I'm going to seize the engineers. Right after repair, I'm going to release the engineers. So that's all there's to it. Okay, so we finished this part of the discussion. Next one, I'm going to introduce some of the exemplary use of output statistic and state variable statistic. Let me take a look. Let's take a look how we're going to do that. First, I'm going to show you how to, since for the base model, we run 3,000 parts. Okay, we want to run 3,000 parts, and we're going to stop the simulation. But if I change anything, I want to see how fast the simulation can be accomplished. So during this, we're going to set up in time for the simulation. So go to your element section, choose the output statistic. Okay. So here, I'm going to change this to time finish or time ends. Okay, whatever you call it. And make sure you choose the unit type is time, and expression, this is the part. Expression is fairly easy. All we have to do is doing run time now. Okay, run time now is the simulation time, is the simulation clock basically throughout the simulation. But since you're using output statistic, it only record the last one for at the end of the simulation. So one observation at the end. So in this case, we're going to see this output statistic in the result. If I run this, okay, now we see the simulation finish, and we can tell we have 3,000 produced, everything. Let's look at the result in the model section. In the model section, you will see the time to finish is 1,336 hours. Also, so this is how we determine. Also, we can command to define a couple state variable. For example, we call this one. We're going to call this one work in progress for TVA. Okay, another one for work in progress for TVB. And these are two state variable, a model level, and the facility. And when we create them, we can add it to the state assignment for here. So here what we have is should be work in progress for model A. Actually, the new value should be WIP for model A increased by 1. Okay, and here what we do is state assignment. Same thing. This is for model B. For model B, +1. Okay, so this is fairly straightforward. And so when entity got created, leaving the source block, we increase the work in progress by 1. And also, when the parts leaving the system, we do the same thing. We can either do it in the state assignment, or we can do it in this so-called add-on process. Since we did it before using state assignment, we're going to show you how to do it in the end of this thing. So here we're going to have assignment block, okay, and we're going to add in to row. So work in progress A equals to work in progress of A minus 1, but this one has to be for example, remember it should be model A. Model A. Okay, if it's model A, I decrease by 1 in that case. Or and add work in progress B equals to work in progress B minus 1, but this one has to be model B. Okay, so if it's model B, then this one going to return by 1, so decrease the work in progress of model B by 1. If it's not a model B, this will be 0, so this value won't change. So this is the way we here we say update work in progress. Okay. And so this is, we can do that, and we can actually see that throughout the simulation how it's going. Let me find a good place for it, and I'm going to put it right over here. Okay, I'm going to call this work in progress A. Duplication here. Work in progress B. So when I run this, you will see this coming through the system. So if they leave, they actually goes down. So you see a work in progress inventory as well. Or you can have animation seeing, for example, some of the status plot you can have right here. You have one means work in progress A, call work in progress A, add another one, call work in progress B, and the label I'm just going to call WIP B. Okay, so here if I run it fast enough, you can see this is coming to go certain level and keep going, and we can determine what is that. And also we can scale this if we want it. Okay, and so this is for 100 hour, for maybe for 500 hour plot, and start plotting. Okay, you can see these two lines going up and down. So this is pretty much the way we keep track of work in progress inventory. But in the case you want to find out what is the minima, maxima, or average of the work in progress inventory throughout the simulation, what we can do is actually stop this, create a state variable statistics. Okay, element state variable state statistic, and we call this one work in progress model A. I'm going to call it a slightly different name so you understand each one is a little bit different from the other. So this is work in progress model B. So this is one we want to include it in the report. So first one, going to tie it into that work in progress A. I defined it. Work in progress A. This one's going to tie it into the variable of work in progress B. I'm sorry. These two variables. Okay. I'm just going to let it run it for a really short time, maybe for 15 days, so you see what happened, so you don't have to wait for too long. Okay. Simulation stopped, and then we see the result on the more model section. You see the work in progress A, work in progress B. Actually, for each one of the work in progress, I produce an average, final value, and the maximum possible. Okay, minimum possible always 0. So you see that on the average, I have a 64 model A in the system. For model B, I have average of 62.3. Final value, I have total 153 in the system. If I go back, and you can see that final value matches the definition of the variable. And then you can use these actually as a part of the experiment you prefer define. For example, in this special station, I define a parameters, and also in the forklift, I will try to determine the carrying capacity, which one is optimal. So to do that, I'm going to create two properties. First is integers, so we call the carrying capacity. Carrying capacity is for the AGV. By default is 1. Okay, and the next one will be, let me add another one, will be the actually the capacity for the special capacity. Special capacity, which is capacity for this special station. Okay, so when we go to our facility, we click on the empty blank space. We see the control over here, the carrying capacity for the AGV. Default is 1. I can change to 3, 5. We can try it later on. This one we can try 2 for this model, then we can rerun. To tie these system property into model property into our system, here I'm just going to change to special capacity, actually right here. So I'm going to refer to whatever special property defined as a special. Also the forklift, I'm also trying to see that the forklift carrying capacity, capacity equals to a variable. So I'm going to try star 302 and see how well that goes. Okay, so these are the things we can do to optimizing my system, either using forklift priority, forklift loading policies, and so on and so forth. Let's look at them in a experiment. So within experiments, you can see that the dwell time is how many hours. For example, I can set up to 4 hours, 8 hours right here. Okay. Pallet size is 10 or 15. Carrying capacity by default is 1, and special capacity is 1. I'm going to create another one. Okay. 2, I'm going to use 4. This is I'm going to using 3, and this is I'm going to using 2. And then we're going to start creating objective function, which we'll call it responses here. So the first one we call it WIP level. Okay. The WIP level is the work in progress on the average for either the model A or model B. So how I'm going to write this expression, for example, we're going to do WIP for model A, which is output, and I want to his average, plus the WIP for model B, and I want to add it to his average. Or I can use maxima and minima and so on and so forth. So these are the WIP level, okay, 4. Or we can add another response, which is the time of the simulation stop. So when it's finished. Okay, we can call it when it's finished. And this one I'm going to call is what? The variable I just defined a few minutes ago, just a second. Oh, let's go back to see what is that. we define an element called time finished, this one, output statistic. So I'm going to using in this experiment called this time finish output statistic. Okay, and time finish is I'm going to change to time in terms of hours, and I can determine is minimize the time to finish. Work in progress level, we can either change to minimum or maximum. Okay, or I can define a state variable called profit, for example. Okay, the profit equals to the TVA finish. Let's look at that. We define those in the definition called, we can have those two in as well. So we set up two output statistics. We call it TVA finished. I explained to you why we're doing that. Okay, TVB finished. What is the now I want to explain the difference between the output statistic and the state statistic. When you define the output statistic in the results section of the model, you only output statistic only see the final value. However, if you define a state statistic on the state variable, it will report the average, final value, and the maximum. So so these are the difference between the output statistic and the work in progress statistic. Work in progress is state statistic. So here I only wanted to using this as a final value. So this is, I'm going to tie this into, I'm going to stop the simulation for now. And coming back this for TVA produce, correct? We have that as also this will be TV produced. Okay, so if I run the simulation a little bit, this is just a short run. By no means this is a final result for your simulation model. I just run it for 15 days. If you see the result, I see the final value for how many TV got finished, TV B got finished, and also I see what is the average work in progress inventory here. Okay, so stop the simulation, reset a couple things. This is 3, pallet size is 10. Okay, this is 1. This is also. So when we go to our experiment, the profit, for example, the profit section will be actually a currency, total number of amount of money, and I will say, well, this is going to be $250 times whatever TVB A finish, okay, its value plus, for example, TVB is $150 per unit of profit. So TVB finish the value. So with that, I should be able to have 3 different objectives, and this objective should be maximum. So also I can specify a lower and an upper bound. For example, I want more than $2,000 and above. So we can start running this. Okay, and now we finish running. I just skipped the running time waiting. You can see that after 10 replication of these comparison, the work in progress inventory level has very different. Okay, in this case, one is 100 100 units in the system on the average of 10 runs. The other one is about 38 units in the system and on the 10 replication run. Finish time is almost the same, and also, but the profit is kind of different. It has drastic difference. So if we look at the response portion, you can see that in the work in progress inventory level, it's different, using a smaller waiting time. So we push through system faster, and when it's finished, it's about the same in that sense. The profit region is about, the same, very different as well. So the scenario 2 with faster, smaller waiting dual windows and higher capacity in the AGV actually produce more profit in that sense. So, so within the same time with the 15-day, the system will be producing more in that sense. The reason when it's finished, because we set the time 15 days, so around this 15 days, they all stop at the same time. So this one is exactly the same. There's no variation because we set an end time. But in your case, if you want to finish 3,000 for each model, this time we'll have a variation with a different setup. Same thing, you can see that in the output pivot grid, similar like before, you can see that each one of the report section has scenario 1, scenario 2, with 10 replication runs. You have an average, minima, and maxima, and the 95% of confidence interval half width. So you can compare statistically for scenario 1 and scenario 2 if they have it significantly different or not. We'll talk about more detail on the statistical comparison later on in the next homework. However, we just want you to know the mechanism, it works, and you can set up multiple scenarios, compare them right here. So this concludes this entire section of number 9 hint video.